Hey, welcome everybody to Back to Basics, Division II Coding for Beginners. And just wanted to welcome Braden, who is presenting for us at ERLC and ARPDC across the province today. He comes from Victoria School of the Arts in Edmonton. So that's the school that links up to the Centre for Education right in the heart of downtown Edmonton. And I'll let you talk a little bit about your school, Braden, because I think it's a little bit of a unique situation for you teaching there. Braden's joining us at ERLC to do a few sessions this year that's looking specifically at computational thinking and coding and how that all fits within the curriculum, very much from the perspective of this is kind of where a lot of people are focusing their learning over the next year or so. So welcome, Braden, and tell us a little bit more about your background, and we're looking forward to today.
Yeah, thanks so much, Jenna. That's great. Yeah, we are, Victoria School is like right in the middle of downtown, but it's a unique school because it's the only K-12 in the district. And then on top of that, from K-9, it's an IB school, so you have to like apply to get in, and then from 10 to 12 it's like an open school. We have lots of stuff going on all the time. There's like a culinary arts program that's really great, that's new. We have lots of students, a lot of them care a lot about the arts, and some of them care about science, but not not very many. So it's kind of nice because the administration just kind of lets me do what I like to do, and they don't really bother me because there's 20 other people ahead of me on the chart of like what's important for the school. So it's really nice that way. Yeah, so what we're doing today, so I've spent a decade teaching there. My interest is in technology and education, and specifically media ecology, which is kind of how relationships change when you add a new medium into your lesson or just into society in general. That's kind of where my specialty lies. And my goal today, I have it set up so that I give you like tools that are basically, you are good to go with those tools starting tomorrow. So I have like a few tools for grades 4, and then grade 5, and then grade 6. So I have some for every grade, and then we will also look into the curriculum specifically and kind of highlight what the new curriculum says at each level. So if you're only teach grade 5, you can ignore the other two, but it will give you a nice context for kind of what the people that help make the curriculum, what they were kind of thinking. And I'm pretty sure that the two people that were my advisors for my master's degree were like heavily involved in the making of the curriculum. So as soon as I took a look at it, I'm like, oh, okay, this matches exactly with what my profs were telling me. So that's good. Yeah, and feel free to just interrupt or put up your hand, and like, especially since there's only one person with their screen on. Hi, Sarah. If you wanna say something or get me to slow down, I'm totally fine with that. I like to just answer questions as they come up.
And maybe I will interrupt.
Yeah.
So just a couple of little like housekeeping things. And thanks, Kim, for switching on your camera too. When there's those of us presenting, it is always so nice to see the people that are in the audience. And I'm sure you all remember that from when you were teaching online as well. So with the understanding that it is the end of the day and you have probably been working for hours and hours and hours already, and maybe just want to switch off your screen, like I get that too. But thank you, Rebecca. It's awesome to have everybody on board. And yes, just interrupt him. And at some point, Braden, I'm thinking you'll probably be sharing the link to the presentation with us as well, right? Like whether early or later or whenever works for you.
Yeah, right after. I can just email you the presentation right after we're done here, so then we can get it out to everybody. Because the presentation has the links to everything already in it, so you just have to go to the slides you like, and then the links are already there. Okay. Yeah, so that'll definitely be.
Make sure you get that.
Yeah. Yeah, this is great. Let's keep going. So computational thinking in general. So this is just kind of an overview. My first presentation was just all about computational thinking, but this is just going to be a quick review of like what it is. It's a specific way of thinking about and solving problems. There's a bunch of main big ideas, of which the 4 to 6 curriculum addresses a few of them. So you're not going to have to teach all of computational thinking all at once for grades 4, 5, and 6. They're very precise in which types apply to which grades. The general idea is that if you can apply computational thinking, it's a habit that you can apply to a bunch of different problem sets that don't just exist in computer science. They can exist in any science. Sometimes it exists in English. Sometimes it even exists in like areas you might not be aware of. It's just kind of getting students into a habit of thinking. So here are the main principles that we talk about that are in grades 4 to 6 curriculum. So big one is pattern recognition and debugging. So pattern recognition, that's huge across the board. Like that is basically what we're teaching in elementary all the way through to high school, is like, what patterns are we recognizing? What can we make with those patterns? And then debugging is, what are the problems in the patterns that we see and how can we fix those problems? So that's a huge one. The other one is abstraction. So that's removing unnecessary details that you don't need. Okay, so the example that I like to use is that Picasso was an abstract painter because he was able to get to the root of the idea without all the extra stuff. Okay, you're looking at a human face. He abstracted what a human face was and then made that into a face, even though it looks nothing like a human face. He has the abstract details there so that you recognize, yes, this is a human face I'm looking at, even if it's a little weird. Okay, so that's kind of the idea. We're pulling out the unnecessary details and keeping only the essentials. This idea is mentioned explicitly in the new curriculum. Okay, this idea of abstraction, of taking out anything unnecessary and only keeping what's needed. And then the last one is in there too. It's also mentioned explicitly. It's collaboration. This is throughout computing science. It's not, I guess it can be talked about quite a bit. But there are so many examples where, like for example, my brother-in-law is a software engineer in the States. And there are examples where part of his job is to look at other people's code and see what can I steal from that. Like there's no such thing as stealing in computer science. It's just borrowing and adapting. There is no one person that came up with the best code. It's everybody is working together to get the ideal situation for whatever you want to do. Okay, so those are the main principles that the curriculum kind of focuses on. The theoretical background for this is based in constructionism. It's a little bit different than constructivism, which you might have heard all the way back in going to university talking about this stuff. Constructionism is, the curriculum is based directly on these ideas from Papert. He was the guy that created constructionism, and it's using student-made artifacts to show growth, learning, and process. So what that means is typically you'd have like design a model of an atom. And through the design of the model of the atom, students can learn, and then they can go back and look at that model and say, okay, this is what I learned, and I know this because I built it, and here were the issues that I ran into while building it. And we can get quite a bit of learning from building the model. The important thing isn't necessarily the end result. The important thing is the process to build the artifact, and then being able to look at the artifact and say, oh yeah, this is what I learned from the artifact, from the actual building. So we can use that idea in the real world, in the physical sense. We are constructing an artifact, we are building a poster, we're building a model of something, or we can do it in terms of code, where we're building an artifact of code that then does something we want it to do. Okay. So I just stole this code. This is code from my grade 9 students. This is just an example of what the kind of code the curriculum expects you to kind of use for grades 5 and 6. It's called block-based coding. We're going to be talking more about it if you haven't seen it before. Don't get stressed out if this looks like gobbledygook. It's supposed to, unless you've actually programmed it. Otherwise, you have to kind of go line by line and then figure it out. This is just an example of what an artifact would look like in the coding sphere. Okay, so that's the theory and kind of why we're doing it. This is a personal anecdote. So I'm a physics major. That's what my major was in school. I was big into physics. And then for a course in university, I had to make a video game. So I decided, okay, I want to make a video game like Asteroid. I don't know if you guys remember Asteroid, the video game where it's like you go shoot little asteroids with a little triangle thing. Maybe not. I didn't like it because it wasn't realistic to physics, and I can be a little annoying. So I decided, okay, I'm going to make a physics realistic version of Asteroid. I'm not an expert in physics, but I know physics 20. I should be able to do this very, very easily. And I found out that until building the game, I actually didn't understand as much as I thought I did. So this is what I mean by, this is what people mean when they say operationalizing your learning. I had to operationalize ideas I had about physics into a game, and it was way harder than I thought it would be. So I'll just show you really quickly. So this was the game I made. We can just expand that screen. And, oh, is it not? Let's actually stop it. There we go. So this is my little Asteroid game. This is the physics realistic version. So if I go up, it'll just keep going on forever and ever and ever because it's in space, and that's what would happen in space. You'll notice there's no actual asteroids because asteroids in the real world are billions of kilometers apart and you'd never actually see one if you went through an asteroid belt. So it's just a bunch of annoying stuff like that I did. But the point is, the learning outcome from physics, the learning outcome from physics 20 is that we need to use two-dimensional motion by adding vectors. We don't have to know what that means, but it was something that I should have known intuitively, and I did not know intuitively. But the only reason I found out that was by building a game that was supposed to do what a physics 20 outcome was. And I figured it out by making this little bit of code, this line of code. And when it came down to it, it was literally just adding things. That's what that green cell, it's just adding things, which I should have got because that's literally what it is. But it took me so long to figure this out in a different forum. And by figuring it out and taking the time to learn it, it took me probably an hour and a half to come up with these 2 lines of code. And then I was like, oh, okay, so this is actually what I'm teaching when I teach physics 20. So that's just a personal anecdote of how creating a model actually did help me learn more about the subject that I should have already been really, really good at. And it really humbled me, which was good. Okay, so looking at grade 4 specifically. So what does the new computing science curriculum look like? And what are some things we can do right away? That's the goal. So this is Div 2 for all of Div 2 computer science. This top part here is the same for all grades 4, 5, and 6. The idea is problem solving and scientific inquiry are developed through the knowledgeable application of creativity, design, and computational thinking. So it's right there in the curriculum, computational thinking. Again, we're talking about abstraction, we're talking about debugging, we're talking about pattern recognition. Those are the main ideas here, and collaboration. So in grade 4, the idea is how can design meet needs? So it's very broad. That's the overview kind of question. And then the general learner outcome is that students examine and apply design processes to meet needs. So that, again, that's hugely giant. That can be pretty much anything. You're designing anything. And here's the specific learner outcomes. Okay, so these are the knowledge outcomes. It talks about understanding problems, getting ideas, planning, creating, giving feedback, cost of materials and availability of materials. It talks about making artifacts, which is going back to that constructionism idea, talking about algorithms or models or blueprints, dealing with complex problems, again with artifacts and algorithms. So an algorithm is literally just, people get freaked out by that word. All it is just a set of instructions. So a recipe is an algorithm. Okay, it's a recipe that you can repeat and make well over and over again. That's a great algorithm. A recipe that only turns out every once in a while, that's a poor algorithm, but it still works sometimes. Okay, so that's all an algorithm is. It can be as simple as a recipe. When we play games, like even just physical education games, when we play soccer, when people play soccer, they are following an algorithm, just the rules on how to play. Okay, so that's all an algorithm is. It's nothing to be scared about, and it doesn't necessarily involve coding at all. Okay, so just wanted to get that through. So those are the knowledge outcomes. These are the understanding and skill outcomes. So understanding, again, we're involving processes that can transform ideas into artifacts that meet needs. So the goal here is making artifacts. So in grade 4, we're making artifacts to meet needs, pretty general. So again, planning and creating, you need to provide feedback to others during the design process. That's a huge part of computational thinking, is the feedback and collaboration. We're testing artifacts. Designing an algorithm to solve a problem. Again, algorithm does not even necessarily mean computers. Okay, you are designing a set of instructions to solve a problem. And examine availability and cost of materials during design. So here's the good news for grade 4. Grade 4 outcomes do not mention computers at all. You do not have to touch computers to get all the outcomes covered in grade 4. There are lots of low-tech options that you can use to get started. Okay, you do not have to touch a computer if you don't want to touch a computer. So here would be my example, like take home, you can do it next week if you wanted to. So you're going to modify a game. So this could be a game like soccer. This could be a game like tic-tac-toe. This could be a game like rock, paper, scissors. Okay. Those games have rules. They have a set of instructions that you have to follow. So the games are basically an algorithm. The students are going to select any game they know well, and then let's say they make 3 new rules for that game. So in their groups, the students are making 3 new rules for that game. Or it could be 1, it could be 2, it could be however many you think would work, okay? The goal would be that students have to make these changes and then play with them to see, okay, is this game still fair? Did I just make rock, paper, scissors, bomb, and bomb always wins? Like, that's not a fun game anymore. Okay, so let's make some iterations. Let's make some changes. Let's tweak things a little so that the games stay fair. So if you want, they can document the changes and write about them as a reflection. So then we can incorporate some English outcomes as well. But if you have the artifact is showing the process. The artifact, like, they should be able to talk about it intelligently because they made it. They know which changes they make. They know which changes they started with. So that is optional to add more curriculum, but you don't have to. And then the project can result in each student playing everyone's game. You can have, or even before that, you can have a feedback day where you play a bunch of other students' games, give them feedback, they go back and make those adjustments. Okay. And then at the end, you have the final games, you present the final games, and then you play them. And then that's it. So that would be an idea. And these are all of the outcomes that covers. All the bolded ones are the outcomes that it covers. So right away, we're covered with one idea, we're covering half of the outcomes for computing science in grade 4. Okay, so that's just like a basic idea, but that's one thing and it's covering a lot of different things. Okay, so same thing here with the outcomes taught. All the bolded ones are the ones that would match up really well. Okay, I think my next slide is grade 5. Yeah, so any questions about grade 4? Any questions about anything I've said so far?
Hey, I have a question.
Yeah.
One piece of feedback I've had when I've been doing that whatever that was, teaching computing science session, is I know a lot of people who come to sessions are like they're trying to wrap their heads around the new curriculum and what that looks like when operationalizing it. What about the teachers who enjoy integrating tech and they're involved in Genius Hour and like all of those sorts of things? Where do you see the grade 4 outcomes might be brought to life by them where they are integrating the technology?
Yeah, that's a really good question. I would start pretty simple, probably more along the lines of what I have for the grade 5 and grade 6. Still starting simple, but going more into instead of making adjustments to a physical game that's played in the real world, I'd say making adjustments to like code that exists like in block code. So there are there's games in Scratch that you can get that are pre-made, and then you can make adjustments to that, or you can even just design your own simple game. I had my grade 9s do that, and it worked pretty well. I'm not sure how well that would go with grade 4. I've never taught grade 4. I've taught everything from grade 7 to grade 12. So that's kind of where where I'm comfortable with. But yeah, I would say you could probably be okay starting with some block code, and I'll show how to get started with that for grade 5.
In the grade 5 part, yeah.
In the
and
grade
if
5.
anyone else has other ideas to chime in, please do.
Yeah, please do. If any feedback for me is great. That's literally one of the outcomes. So I have to be good at taking feedback too.
I actually really like what Braden said about them taking the code and tweaking it, because I know with the makerspace type approach to things, so much of that is tinkering. And to give them something to start with that they can then tinker with, it seems to me like a safer space than just doing something totally from scratch. No pun intended.
Yeah, no, that's completely right. And like tinkering is another like cornerstone of computing, computational thinking. All right. Oh, it's already 4:30 almost. Okay, grade 5. So Div II computing science, if that part is the same, that hasn't changed from grade 4. But now in grade 5, in what ways can design be used to help achieve desired outcomes or purposes? Very similar to grade 4. But now we have students apply design processes when creating artifacts that can be used by a human or machine to address a need. So now we're getting more into computers. I don't think you can get away with not using computers in grade 5 and 6, but with the wording used in the curriculum. But that's just my opinion. So grade 5, longer, more knowledge outcomes in this area, kind of what you'd expect. These are the main ideas. I think I cut a couple like examples just to fit everything on the page, but these are for the most part, these are the knowledge outcomes. So it just talks about what an artifact is anything created by a human using a computer. So now it's nailing down what the curriculum expects of an artifact. Yeah, so we can create algorithms and translate them into code. So we need to be able to translate algorithms into code at some point. We're doing multiple iterations again. It mentions specifically improved through collaboration. It talks about usability. How easy is it? And then it gets into some specific coding language, like a loop. A loop is a repetition of instructions used in an algorithm. Okay, so we're starting to get into actual ideas here. There are many ways to code, including using visual block-based languages. Like, I'm pretty sure that's just them hinting, use a block-based language, please. The reason why, I'll show you what a block-based language looks like. And if there's time at the end, we might even be able to kind of play around with one. It's basically a way to get kids to code where no mistakes can happen because of their typing. Okay, so normal, typical code, what you see on like movies, you have to be so specific. If you put a comma in the wrong place, it could mess up everything. Block-based coding gets rid of those errors. So if there's an error, it's usually something that a kid chose on purpose and is making a mistake now, rather than, oh, there's a minor mistake and it's making everything go haywire. Okay. The kids have to know that code is any language that can be understood by and run on a computer. A computer cannot think for itself. A lot of times students think that that's true, that computers just kind of do everything on their own, but as of today, that's not the case. And there's a bunch of design processes, aesthetics, reliability, functionality. So the understanding and the skill and procedure outcomes. So I'll go through these kind of quickly, but basically relating one block of code to a specific outcome is something that they have to be able to do. They have to explain what will happen when single or multiple blocks of code are executed. So again, it's using the word block in there. Translate a given algorithm to code using a visual block-based language. Algorithm including a loop. So now it's using, so you have to at least get them to be able to use loops in a block-based code. That's the general idea. Yeah, everything else is multiple iterations, artifacts, stuff we've already talked about. Now we're up to, they have to build an algorithm using a block-based code, and it has to include a loop somewhere. Okay. So here are the high-tech possibilities that are available to you. The curriculum says block code, you have to use block code. So here are some ways we can do it. I have two ideas for you. One is hour of code. This might be something that you use this year before the new curriculum starts, just so you can get a hang of it. And then I have something called code.org Express course. So I'm going to go through both of those. And again, I'll share these with you so that you'll have the links to them. You'll have everything that I have. So hour of code are pre-made games that can be done in an hour. They have a bunch of different things. If kids like Star Wars, there's Star Wars. If kids like Frozen, there's Frozen. It's all based off of, here, I'll just show you kind of what it looks like. So hour of code for students, we can explore the different activities. So we have a bunch of different things here. All of them have grades. All of them say whether it's block-based or language-based. You can control by length. You can control by topics. When I've done this before, all I've done is shared the link and say, as long as you're doing something on this website, good enough for me. Okay, so do an hour of code, that's great. So there's a lot of there's endless choices for the students to have. I know Minecraft is big, so there's Minecraft in there. Like pretty much the makers of this are on purpose trying to incorporate things that students will like, so that way they have at least a friendly introduction into the ideas of coding. Okay. Yeah, so that's hour of code. It works really well. It even separates by grades. So grades 2 to 5, I can just go to grades 2 to 5. Yeah, and there's the Star Wars. There's a bunch of different ones. Usually kids talk about which ones are cool and which ones are lame, and then they figure out which ones to go on themselves. Yeah, this is free. This is total, like everything I'm sharing with you, unless I say there's a charge, it's free. There's only one thing I mentioned that has a cost associated. All of this is free. The kids don't need to sign up for an account. They literally just click and go. So it's really nice that way. Yeah, you can also separate into like, oh, beginner, who's a beginner coding, who's already done some coding before, which is really nice. Yeah, they've done a really good job for Hour of Code. Okay, so that's Hour of Code. Here's the code.org Express course, which is from the same people as Hour of Code. And this is what it looks like. Okay. The Express course has different things where it just builds off of ideas. So the first one's programming with Angry Birds. You get started, it shows you like what one line of code looks like, how to get that into the program, how to press run on the program, how to stop the program. So this is built with heavy scaffolding in mind, so you don't have to do any of that. Okay. The nice thing about the Express course, actually, let me just go back here. It has pre-made lessons. And you have, if you start a teacher account, again, free, you get to see every student's progress. So basically, it's very similar to Google Classroom. Every student joins a class, and then you select which lessons you want them to do. And then having a teacher account, it lets you see the answer key for every level. So even if you're not comfortable with doing everything, even if you're not comfortable at all, at least you can go in and see from your end, okay, this is what it's supposed to look like. At least I can guide my students and give them hints along this way, rather than I have no idea what's next and I'm just starting out with coding myself. How am I supposed to help them? Yeah, so it does have like an answer key for you, so you don't have to freak out about not knowing an answer if a student comes to you. And the ones that I would recommend, oh, where is it? Back to here, would be, so you have sequencing, you have sprites, events, and loops. So if they just do all of these from lesson 1 to 13, that's it. They now should be able to do everything mentioned in the curriculum, including loops. Okay. So what you can do as an instructor, when you have your own account, you can modify the Express course to only include 1 to 13. And then you can also see where every student's progress is. Okay, so this is assuming that all of your students have access to one Chromebook. This works really well on a Chromebook. You can partner up if you don't have enough Chromebooks. That works as well. Sometimes that works even better because then students kind of figure it out between each other. But yeah, then you make your own course. The students go and you can kind of see, okay, who's doing really well at this, who's a little not so quick, and then you go in and help that person one-on-one. So it's kind of nice that way. Yeah, if we have time, I'll show you like exactly what that looks like, what the code.org, and I'll even let you guys play around with it and see how it works for you. So I was just thinking of using the code.org Express course from lessons 1 to 13. These are the bold ones are where it covers. Okay, so again, it's not going to cover everything. This is not like a silver bullet, like, oh, I'll just do this and then that'll be good for the entire computing science curriculum. But it does cover a lot of it. Because it talks about how can you make this code more efficient? Are there blocks that you need to take out? If there's blocks that you can take out, well, that's abstraction. We're getting rid of things we don't need. Can we take algorithms and translate them into code? It specifically talks about loops, so that's covered. And then the skills and procedures and understanding. So we are hitting still about half of the curricular objectives just by getting them to do this over a few days. Okay, grade 6. Before we go to grade 6, is there any questions from grade 5? Okay, I know there's no questions because you guys just want to play around with coding. I know that's why. Okay, grade 6. In what ways are abstraction, design, and coding related? So now we're starting to actually get into computational thinking language. So students examine abstraction in relation to design and coding and describe impacts of technologies. So this one is a little bit harder to do half of the outcomes because it talks about describe impacts of technologies, and you're not going to be able to rely on a website to do that. You'll have to talk about that as a class. You'll have to discuss those kinds of ideas. Whereas the other half, the abstraction, designing, and coding, you can do that with the coding. Describing impacts of technologies, that's going to have to be good old-fashioned teaching. Okay, so here are the knowledge outcomes. Again, yeah, we know this now. Determining what details to keep and what to ignore. Removing unnecessary details. Identifying important information. All that stuff goes under abstraction, which at this point, you three are experts at. Impacts of computers, coding, or technology may be intentional or unintentional. So that's one where you'll have to have a discussion about it. Is every time you use a phone or a computer, has it done what you meant it to do? What about for society? Has everything we've introduced to society, has that been good or as good as it's supposed to be? What are some negatives about it? It talks about abstractions can make daily life easier. Yeah, no, that's exactly right. Yeah, it's really nice that it builds on every year. Like every year, it's just one little baby step more. So yeah, it's really good that way. Yeah, so now we have more things. If we talk about just the coding, now we have sequences, we have conditionals, and then we have loops again. So conditionals are really simple. They're if this, then that. So I know it sounds complicated, but it's just like, for example, if you're making cookies, if dry, add water. That's it. That's all an if else statement is. If dry, add water, else don't add water. That would be an entire like thing of code. Okay. Sequence structures are ordered set of instructions within code. That's not anything new. That's what we're building on. We are building sequences into the code already. Yeah, no, exactly. Simon says. If I say Simon says, do it. If I don't say Simon says, don't do it. And then that's the whole idea of the game. Yeah, thanks. That's a great thing to say. Okay, use of computers, coding, and technology can have impacts that are personal, social, environmental, and economic. That is something you have to involve the students with and not something you can get from just getting them to do something on a computer. So again, again, these are the same ideas, just in skills and procedures and understanding, possible impacts, discuss how computers, coding, or technology have had impacts, using a visual block-based language to design code that includes relevant design charges. All that stuff is kind of getting repetitive at this point, I'm sure. So here are the same ideas. Here are 3 ideas. One of them is building on the one from grade 5. So grade 5, we did lessons 1 to 13. If we do the express course, but include 14 to 19, now we have conditionals in there. Now we have if-else statements right there. We have while loops, okay, which just means while something is happening, do this loop, do this continuation of something. Then we have conditionals until loops. That means until something happens, keep looping. Okay. Until I say stop, keep looping in your, like, running around the gym. That's all it is. So all we're doing, so this is nice too, because you might have students that might not have had this experience, right? They might not know about computational thing. They might not know about coding. They might be coming from a different district. Who knows? The nice thing about this is that you can get them started at level 1 if they haven't done it. If they have done it, you can get them started where they left off, or start back at 10 so they understand what loops are, get a little bit of a refresher. Okay, so that's up to you as a teacher. You can choose which lessons you're going to do. Okay, so that would be a good jumping off point. Something else, if you're feeling like, okay, it's grade 6, I want them to do like a big project. I think they're ready for it. That's what Scratch is about. Scratch is a block-based coding that is more of an open sandbox. It's everything code.org can do with very similar language. And this can be really good for simple things or more complex things. It's really up to you to figure out how can I use Scratch. If you're curious about how can I build a Scratch project, that's what my next thing is about, my next session. So just come to my next session if you want to learn more about that. But Scratch is the one where I had the game, where it can look a lot more complicated, where you have different sprites. Sprites are just things that kind of move around, and each sprite has different code attached to that. We can have, so it can be very complex. This is obviously not something that you would give your grade 6s to do, but you can do side scroller games like Super Mario, right? We can do other games. They can get them to make a Pong game. Okay, something that's pretty simple, pretty basic, but you can do a lot of things with Scratch. It's basically code.org, but you have access to all the blocks all at once, whereas code.org hides the blocks you don't need, so you can't make unnecessary mistakes. Okay. Again, Scratch is free. To save an idea, you have to have an account, but it is a free account. So there's nothing there, and it is based on like MIT makes it. So it's a very well-made, well-made product. This last one is, if you have the money, I cannot recommend this enough. If you don't have the money, just wish you did, because it's really good. It's Lego Spike Prime or Spike Essentials. So Lego came out with a brand new computer kit, a Lego robotics kit, I think in 2020 or 2021, and it was the first one that had come out in 15 years. So what is really nice about Lego is they make sure everything is like perfect before they release it. So I spent the summer helping a class where all we did was teach upcoming teachers to use Lego robotics. It's a really cool class. But all they do, here I have the link, but it's already here. It comes with a kit that has a robot and a bunch of motors and a bunch of sensors and some Legos. And they build the robots in the units. So these units are already pre-made. You don't have to do anything to them. This runs off of Chrome. So you can just use them in Chromebooks, but it can make a bunch of different things. So for example, you can have a race with a little hopper thing. You can have a grabber. Let's go back to when you're doing, like, they have different themes. So like making a business, you can make a safe. So students have to make a safe, and then it only will work if there's certain combinations on the safe. There's one that's really cool. Something breakdance, you get something to repeat. So this one is teaching loops. Then you have something, little robot that measures the accurate wind speed outside. So it like in real time, it measures what the wind speed is, and depending on how windy it is, the robot will like go way back or just be standing straight up. This one's called Brain Game. It eats different Legos, and it tells you like out loud what color the Lego was, which is kind of cool. So based off of sensors, it gets to do all these different things. If this is too advanced, there's also something called the Spike Essential Kit, which is more meant for grades 1 to 2. For some of them, these are grades 3 to 5. So we have carnival games. So you can do mini golf or bowling or the hockey game or a little maze. All these different setups that are included with the kits that you can use. So they're really, really great. They're pretty expensive. But if your school can get them or get a grant to get them, it's well worth it. But that would be the third thing I would recommend for grade 6. And then, yeah, again, I didn't assume, I'm just assuming you're using the co.org. So if we're just assuming you're using co.org, again, you're hitting less of the curriculum than you were before, because now there's a bunch of discussion topics. Yeah, Black Friday deal. Good luck with Lego and getting things on sale. Yeah, so these are all the knowledge outcomes. Just if you did the free levels 4 to like what did I say it was? Co.org 14 to 19. So we're still hitting quite a bit of those outcomes, just doing one project. Okay, we have a little bit of time. I think we can probably stop the recording, and then we can we can just share the co.org Express course.